Hello everybody. So I am Dr. Sergey Sarkisov, and I want to take a look into just numbers today. So in other words, I call this arithmetic, okay? Arithmetic. And this is before algebra. This is before algebra, this is before trigonometry, calculus, any of those subjects, let's say, as far as what you would be learning in that sequence. However, arithmetic, okay, is a big key to all of the fields following. Number theory actually is a big thing that sometimes directly results from knowledge of basic arithmetic without even knowing some things later on from trigonometry or whatever. So let's look at this, arithmetic, right? Well, this is basically what I consider arithmetic is numbers and operations on these numbers. Okay? Numbers and operations, okay? Well, what do you think of when I say numbers? What do you think? All right, when I think of numbers, I'm thinking, well, here I am by myself, right? 1. The number 1 comes to mind. That's a big number. That's a key number in mathematics. I'm going to write it. The number 1. Okay. Put it in a little set notation. This is a braces. Okay, so we have parentheses, we have brackets, and then we have braces in mathematics. It's a set of these numbers where I'm going to say 1, and then guess what? I'm going to start counting. Say students are coming in, 1, 2, 3, 4, 5, counting all of you here, right? And so you have 1, 2, 3, 4, and so on and so forth. And you know what I was doing is that's an operation actually of counting, counting. And these numbers, one name for this set of numbers, all these 1, 2, 3, 4, 5, they're called counting numbers. Okay? Another name, if some of you may know this, it's natural numbers. It's another name. And in mathematics, notice the names are a lot of times these names are basically, very much English or words that you would see in when writing an essay in an English class, right? Natural numbers. Some things are natural, they make sense to us. We see them in the nature and the real world, right? And in many things in mathematics, you'll see the words, and soon enough I'll tell you whole numbers, they're whole. Real, things are real or maybe rational, it makes sense, versus irrational, doesn't make sense. So we'll look into those numbers soon enough. But look, these are called counting or natural numbers, okay? And numbers, and so these are, you can denote it with a little bolded or kind of 2 lines here, N, capital letter N for natural numbers, okay? This is denoting the set, this whole set of numbers 1, 2, 3, 4, 5, and so on. Now, what's another big number, and you think of it this way, I usually say, hey, look, when you take a class on psychological development, maybe, psychology, when you're talking about cognitive development, right? As a young child, in fact, as a baby is even born, let's say the baby's getting fed, one time, first time something happens, first time the baby is hurting or upset and crying, or first time baby says something or sees the mother. Anyway, so that's the number 1. I would represent that kind of idea with first, number 1. And then, 2, 3, 4, 5, you get fed again and again, and the baby is conceptualizing these numbers, whether or not it's seeing, of course, mathematically exactly what it means. What does it mean to know math, right? What does it mean to know numbers? I have a dog, and the dog, I think it kind of counts. Well, let me explain how. I give him a scoop of food, and then he's waiting. He's not eating that scoop of food. Why? Because he knows I'm going to feed him 2 times. 2 scoops. I usually give him 1.5 scoops, and he's waiting. When am I going to give him that other half? He looks up at me like, hey, where's my other half of the scoop? Now he's hungry, he's starving, he's a chocolate lab. Guess what? That's pretty cool, right? He's waiting. I put that second half, that little second half scoop, and he jumps at the food, but he's waiting for me to give him that second scoop. That's pretty cool. Again, if you are interested in dogs being able to count, I don't know, that's something like 1 and 2, right? Not just 1. Anyway, so let's go on to add another number. What if the baby is hungry, doesn't get fed, missing something? Well, before the missing, let's say this, 0. What if nobody comes in? And I'm just basically, like sometimes now, I'm talking to myself. I feel like a total 0 loser. And anyway, the 0 is a big number, and let's add it to this set. of numbers. So let's say 0 and then 1, 2, 3, 4. Because it's all basically the same thing, just add a 0. And these numbers, okay, they're whole numbers. They're whole pieces. You have. I mean, obviously, I'm not talking about half students or anything. You're a whole person. 1, 0, 1, 2, 3. These are whole numbers. So sometimes we do not make a distinction between this set and this set. And sometimes mathematicians will say these are whole numbers. However, most mathematical materials will represent the set 1, 2, 3, 4, 5, and so on, counting in natural numbers. And this, adding a 0, becomes a whole numbers set. And you can use a W like that to represent that. That's one symbol that can be done. A bolded, let's say, W for whole numbers. Now, what happens later is you start losing. You're missing something. You're getting in debt. Students are leaving, and you're getting the negative numbers. The same ones, but negative. And so basically imagine you have negative, something small, and then negative 2, negative 1, 0, 1, 2, 3, right? And so on and so forth. But you have these negative numbers, all right? And what happens when you have negative numbers? You're losing, you're in debt, you owe somebody something. It's kind of like negative, right? This set of numbers is kind of a word that's not usually used in English or in literature. This is more a mathematical term, I would say. Integers. These are integers. Integers. Okay. And you know these with the letter Z. You may wonder why Z. That's kind of bolded Z. Z in Germanic kind of word is, there's a word Zentrum, kind of central numbers. And I would think of it this way, like centered around 0, plus or minus 1, plus or minus 2, and so on and so forth, integers Z. And then what do you think happens? Like, for example, my dog, right? His name is Snickers, by the way. He's a chocolate lab. What happens is this. I feed him 1 scoop, and let's say I'm feeding him 3 scoops a day. All right, so I feed him, or like, let's say I give him 3 times a day. So I feed him once, I feed him twice, and then I forget to feed him that 3rd time. Snickers will not forget that. He will know that. He's hungry. And when he's hungry, he knows what's up. So it's interesting. Right? Like, I don't know if every dog does that, but Snickers is looking at me and he's complaining and he's coming up to me with a snout and pushing me around. He has gotten fed 2 out of the 3 times that he deserves. 2/3. That's a what? That's a rational number. Makes sense to him. Rational. Makes sense to us. It used to make sense back in old days and back millennia. All right. Rational numbers existed. Let me give you an example of rational numbers. 2/3. A fraction is basically fractions. Now, of course, yeah, these are also, look at that. So what is 2? It's 6/3, right? That's a rational number. As long as you have an integer over an integer, let's do a -5/2, right? Negative 11/3, right? All of these, and they're always between them anything you want, right? You can always get a fraction between a fraction, 2 fractions. So these are actually, this is a set of, it's interesting to show later, these are actually countable. Countable, which is basically kind of like 1, 2, 3, 4, 5. Very difficult for us right now to see that, but there's definitely infinitely many of these. Some, anything here and there. So many more numbers you can always put there anywhere. And then it goes on with fractions. Let's say this is 2, and then we can do a decimals. We can say 4.182. Anything that ends or repeats, or even a 7.333, and so on. Anything repeating decimal or stops, a finite decimal also turns out to be eventually, you can make it in a fraction form. And this is, what is that? That's denoted, these are rational numbers. They used to be the only ones that made sense. Rational numbers. And if anyone knows, the rational numbers, another word is basically, their division is quotient, right? Not product, but quotient. And so there's a Q like this that's used for rational numbers. Okay? And then you may wonder, well, that's it, right? Calculator, I call them calculator numbers or fractions also. Calculator numbers or fractions. But let me explain one thing. What is not a rational number? What doesn't make sense or didn't make sense at the time? Well, what about irrational numbers, right? Like, what is that? What is that? Because there are some. Let me show you. Imagine, okay, and this is actually from a philosophy book that I read, I believe by Plato. Plato's Socrates. So here there was an idea. Let's say, okay, and I remember the story goes somewhat like this, I'm not sure exactly, but you have maybe, let's just imagine some crop like corn, and corn grows that year, maybe in a field, a square field of 1 by 1. 1 kilometer by 1 kilometer, or 1 acre, 1 by 1, you get an acre. And then, so anyway, the next year, a surplus rain, all this good weather, and you have doubled. The corn is doubled, but everybody's happy. You have more food to eat. And so this is the first year, and the second year, you now have a bigger field, right? And so basically, let's say just 2 of these blocks, right? But the king wants, obviously it didn't grow in 2 blocks, 2 squares like this, right? This is basically how much you have corn in the next year, so you have more. But the king, let's say the king of the land or the ruler, says, hey, look, and the king's pretty smart, himself at that time, right? So he says, okay, I want this to be a neat square, field. What is this? I don't want 1 by 2, right? That's 1 by 2. I want something by something, side by side. And so this, you want it to be a square, okay? Square field. And the square, same area, right? This is 1, 1. So this is area 2. This was area 1. This is area now. 1 plus 1 is 2. And so you want a square like that holds all of this corn, but it's a square, okay? And so the king says, hey, I need a mathematician. I can't figure this out. It's kind of tough. I mean, I'm looking at all these rational numbers. King was pretty smart. He's like, hey, I need some help. Sometimes asking for help is the smartest thing you can do, with especially what you have to use at that time. So, okay, king says, hey, look, here's a side, and I want this to be 2. All right. Somebody comes up and says, hey, king, look, we can do 1 by 1 still, but the problem is that's equal to what? 1, that's too small. It's less than the 2 area. So obviously we need a bigger side. King says, somebody says to a king, hey, look, you know what? I can do 2 by 2. It will fit it. 2 by 2, but that's 4, right? That's 4, right, everybody? 4 is what? That's actually bigger than 2. King kind of wants exact. King is, we need to not lose anything or gain anything to have too big of, fencing or whatever. We don't want to waste any material. So look, anyway, somebody says, hey, look, I see 1.5 times 1.5, 1.5, 1.5, or 3 halves, 3 halves. What if you multiply that square at 9 fourths? 2.25, 2 1/4, right? And so, but that's too big. You don't like that. We don't like that. So it's still too big. Try 1.4. 1.4 squared, basically 1.96 if you look into that. We could do that without a calculator. People could do it back then. And this is going to be less than 2, still not big enough. King is like, well, you know what? I want exact. 1.4 is not enough. Somebody says, hey, look, let's try 1.42. If you square this number, it's a little bit bigger than 2, in fact. And so, hey, we don't like that. 1.41, I believe that's a little bit smaller so if you square it than 2. So you start approximating. You can do that, and plus you can approximate more and more, but never exact, unless you ask somebody like a mathematician, basically, like I can say like a magician who makes stuff up, and mathematicians sometimes are like that. So, mathematician, what do? And mathematician says, hey, you know what? We're going to make something new up. This doesn't exist. I'll prove it. I mean, as far as you can prove, this is not this s. Okay, this s, when you square it to 2, that's not a rational number. You can prove that, okay, because you can, a little argument that I do in pre-calculus classes basically shows by contradiction that this s is not, if you assume it's a rational number, it's not going to be. If it's a fraction, integer over an integer, it turns out it cannot even be that when you square it, you get a 2. Because even on the right side and left side, and then it can't be even at both sides. Anyway, so you'll see, you can try that argument. Why s cannot be a rational number. But we're trying to do rational. Even 1.42, you know what that is? That's 142 hundredths, right? So it's still a rational number. You can do that as 71 over 50, right? Like you can do different kinds of ways to do a fraction format of 1.42. Anyway, so the mathematician says, you know what? We're just going to make up a new sign called the radical. I mean, now we call it this way. And we're going to call this the square root of 2. Square root. Square root of 2, it's irrational, and if you multiply square root of 2 by the square root of 2, that's going to be our 2. And we're just going to, this is just a new number, and we're going to make it up, and we're going to do, basically the definition of this is if you multiply this by itself, you get back the 2. Ta-da. And it seems like, well, if you make something up like that, that doesn't make sense at the time you're, that we were really, the mathematics at that time did not have square root of 2, well, what's the point? You know what's the point? When a mathematician makes something up, a lot of times, imaginary numbers, complex numbers, and further on, whatnot, you get a lot of beautiful results that help throughout, even in the natural world. Okay? So that's interesting, right? That this happens to be, sometimes when you make something up, okay, it happens to help with, like for example, trigonometry, if you do, or imaginary numbers, like let me just quickly say that. You don't see, imaginary, you don't see that like just jumping around in nature, kind of, do you? In fact, you kind of do. Like let's say you do physics and you talk about electromagnetic waves, photons, light, light waves coming at you. You know what? You can do complex analysis actually ties into the real world somehow. It's really interesting. So take a look into that. If you make something up, you can make up some things too. For example, people say, I'm going to give you a hint a little bit here. People say you cannot divide by 0. I've done a little research about, hey, I'm going to let myself divide by 0 and call it some number. Okay, I don't want to go too much into that. It's a little kind of private research spectrum for me, but anything can happen. What is the word impossible? Not in mathematics, right? So anyway, with that, let me go ahead and give you some other, besides the square root of 2, what other numbers are not rational? You can do, for example, square root of 3. Now, square root of 4, no, square root of 4 is actually a 2, so that's not, right? Square root of 5, maybe. You can do e, that's an Euler's number, 2.72, but this is actually also an interesting number. It's basically for logarithms, a number that also will be irrational. Pi, the circular number, right? Circular number like pi, r squared is the area of a circle. How many radians do you go around, right? Pi radians, 2 pi radians to get the circumference and so on, the perimeter of the circle. So pi, and then you can do more. You can do like, for example, square root of 11 minus pi, right? Whatever. Let's do square root of, make it bigger a little bit. 19 minus, let's do 39. So these are all. This is an irrational number, 2 irrational numbers. Subtracted, it's going to be irrational. So it goes on. And this is maybe you can do negative. You can do that negative 3 root 5, negative 11 over 3, square root of 2. All these, whatever, go on. These are all irrational numbers. And when you have a square root of something weird, or the calculator is not really able to finalize an answer with any pattern in its decimal form, like 3333, then you have an irrational number. Irrational. Okay. Irrational number. And sometimes irrational numbers, you can say the complement of Q, the reals, basically what are not the rational complement of the rational, the irrational. That's one way to think of it. And then let's go on. This is a little tricky because complement from what, right? From the real numbers. You don't want to talk about all of complex numbers because it's a little, that wouldn't really work. So anyway, let's look at this now. Let's go on to, okay, we have these rational, we have the irrational numbers. We have all of mathematics, seems like. Put it all together. Rational. And you can do union, meaning use this or, take a number from there, the rational or irrational, and that number is going to equal to some number that's going to be called real numbers. And the set is R for real numbers. Anything, basically a calculator number, anything you get, you plug it in and you get something, okay, that's going to be a real number. When it says error, that's not a real number. When it doesn't say error, it gives you something in the calculator, that's a real number, real numbers. I call these, so this is fractions right here. I call these, so this is fractions. Quotient, right, fractions. These are, I call calculator, this is my word for using it. In class, is calculator numbers, okay? And finally, well, almost finally, there are a few other things you can do. For example, somebody says, hey, I say, hey, solve the equation. Let me show you. Let's solve the equation. X squared is equal to 9. For example, I'll ask that question a lot, and students say, hey, I know what it is, and I'll say, what is it? And they say 3. That's not solving this equation, because actually there are 2 numbers. This is a quadratic equation. We're not really doing algebra at this point, but just showing you here. The answers will be x is equal to, negative 3 or 3, right? Because both of these numbers, negative 3 or 3, when you square it, you get back a positive 9. Now, so let me just say solve, and you get this as the answer, right? Now, that's not really what I'm trying to show you. I just want to show you there are solutions to that. But what if I asked you, and these are, by the way, these are integers, right? -3 and 3. What if I asked you, hey, solve another type of equation? Solve x squared plus 1 equals to 0. Well, if you solve that, if you're used to a little bit of algebra solving that, okay, what is that? Let's isolate the variable. X squared is equal to -1. Hold on, wait. Any real number, any number I take, negative, positive, when I square it, what am I going to get? It's either 0 squared is 0 or it's positive. That's a -1. Negative. We don't have that. That's it. We're done. Error. Problem. Get out of here, right? No. We're going to make up, mathematician, what do? Make up a new number. This new number, x is going to be, well, let's call it plus or minus, but forget the minus there. So the square root of a -1, right there, that's square root of, if something squares -1, the square root of -1 is that, if you square it, get -1 back. We're going to call this number I. Okay? Just make it up. It's imaginary. It's not real. It doesn't make sense. We can't even visualize it. It's imaginary. Imaginary numbers. Okay? Cool, right? That's another number. And actually, this is part of a complex number. It can be it's something we can use to get a lot of beautiful results later on in mathematics and in the world that uses complex numbers. Imaginary, let me explain complex. Imaginary, so for example, anything I, square root of a negative anything, will be like, let's say I, right? Or square root of a -4, which is 2I. Let's do square root of -4 is 2I, right? Or 7I, square root of -49. Or maybe even a square root of 50 negative. So 5 root 2I, right? Or square root of -80. Try that, okay? And go on and on and on. -1's possible also. What about -2I, right? Or, let's say negative square root of a -10. So all of these numbers, somehow, these are called imaginary numbers. Imaginary. And maybe I can use the little letter like that, I. Depends on, sometimes this is irrational, sometimes this is imaginary. Let's use I for the imaginary. Finally, if you put together real and imaginary together, it's a little different, right? Because real is real, imaginary has an I, square root of, let's see, so if I do imagine the real, the set of numbers, real and imaginary, it can be just real, it can be just imaginary, and imaginary combinations, combinations, okay? Basically, some real number, A, plus another real number times I, though, right? A, B, I. These numbers, and these numbers A, B, I, where A and B are real, and then the I, of course, is the imaginary square root of -1. These are real, and I is imaginary. I equals square root of -1. These numbers, this set is called, it's denoted with a C. They're very difficult to understand at that time especially, or at any time when they're invented. These are called complex numbers. And this is basically where we are today in the world of mathematics. That any number, in fact, if you multiply two complex numbers, you will have a complex number. Take a complex number to a complex number power, complex number. A lot of different things. You do whatever you want to do with it. Usually, almost always, unless you divide by 0, which is, again, I was saying some kind of tricky stuff, you have a complex number. All right. So these are number sets you want to talk about. Again, let me just summarize quickly. You have the natural numbers, the whole numbers. You have the integers, right? You have the rational numbers, the fractions. You have the irrational numbers, the ones you cannot make a fraction. You cannot say integer over integer. Now, again, we do not want to divide by 0 ever here, right? Never divide by 0 in what we are doing, okay? The real numbers, calculator numbers. Anything have a calculator, that's not error, that's the real numbers. And then we have these imaginary with an I, right? Square root of a negative something. And finally, putting those together, A plus BI. For example, 3 minus 7I, 4 plus 2I. All those, square root of 3 minus the square root of 7I. Just a 5 or just a 2I. All those real imaginary combinations, they're all in this set, complex numbers. All right, hopefully you enjoyed that and got something out of it. Okay. Everybody have a great remainder of the day, and I look forward to seeing you next time.